Okay, we've seen a couple of rules for finding derivatives of common functions and of different types of operations we could do to those functions. So now we take a look at a different type of derivative, which is called the implicit derivative. So this is the first part of reading quiz number 13. There will be a second video later. So first of all, let's talk about what an implicit function is. That's a function that has not been solved in terms of one variable alone. That's opposed to an explicit function. So y equals x squared plus 4 would be an explicit function because we've solved for one variable, while xy plus x squared sine of y equals 4y squared would be an implicit function. We want to have implicit functions because they're just different ways that we could combine variables. We don't always have to solve for one variable, and we need some sort of a way to find the derivative of those implicit functions. So this concept is really just an extension of the use of the chain rule. So remember that dy dx, or our derivative, is our ultimate goal. The derivative with respect to x. All right, and that's what we're looking for. We talked a little bit about that in the lab, hopefully. All right, so, as opposed to finding dx, dy, or anything like that, we're finding dy dx. So here's an example. Off to the right here, you can see the graph of x is equal to y squared, an implicit function you may know as a sideways parabola. It's not a function, really. It serves an important equation in math, not a function the way that we've defined it in pre-calculus. So let's say that we want to find the derivative without having to solve for y. The procedure will be something like this. We take the derivative of both sides, derivative with respect to x of y squared, and the derivative with respect to x of x. The derivative with respect to x is really the easy part here. The derivative of x with respect to x is just going to be 1, dx over dx. Derivative of y squared, however, will be 2y dy dx. The reason for the extra dy dx is because we need to respect the x. Our variable is y. Y is presumably some function of x. We don't know what it is necessarily, okay, but we know that y and x do relate in some way. So to take the derivative of y squared, think of it as taking the derivative of the outside function first, something squared. Derivative would be 2y, times the derivative of the inside function, y, which is a function of x. So that's why we get an extra dy dx. Dx dx, as I said just a minute ago, reduces down to 1. So we're just left with 2y dy dx equals 1. And then we can isolate for our dy dx. Dy dx is equal to 1 over 2y. And typically we will leave our derivative in that form. So let's talk again about why we have that extra dy dx at step number 2. We are saying that y is a function of x. Y equals f of x. So one way that we can consider that is if we replace all of the y's with f of x. Derivative with respect to x of f of x squared, just like y squared. And then the derivative with respect to x of x. Well, if you think about this problem right here is a chain rule problem. Derivative of f of x all squared would be 2 f of x times f prime of x. That's the chain rule. Our outside function is something squared. Our inside function stays stays the same for the time being. Then we take the derivative and multiply it by everything else that we have. If we isolate and solve for f prime of x, the derivative, we get 1 over 2 f of x. And hey, what did we say f of x was? F of x was y. We will prefer to use dy dx instead of f prime of x, because that dy dx notation will help us in the future when we deal with differential equations. So here's an example from an old reading. Consider the equation xy is equal to 4. This is a rotated hyperbola. We want to find an equation for dy dx using the procedure we just talked about, and our equation may be left in terms of x and y. So careful, we need to notice that on the left, xy is a product. Think of it as x times f of x. So Again, with product rule, we consider our two functions. We've got x and we've got y. And we need to take the derivative with respect to x of each part. What I said before was the derivative of x with respect to x is just 1. Derivative of y with respect to x has a specific name. We call it dy dx. Putting that all together, we get x times dy dx plus y is the derivative of xy with respect to x. Now, we're not done yet because we want to solve for dy dx. Remember, the other side of this equation was the constant 4. So basically, x dy dx plus y is equal to 0, the derivative of 4. In order to find out what dy dx is, we need to isolate it, just like we're solving an algebraic equation. We move the y over, make it a negative y, and we get dy dx is equal to negative y over x, which we can leave in that form. A little bit more complicated example here. Consider the equation x squared minus xy plus y squared is equal to 7, which is given below. This is a rotated ellipse. So this is a multi-part question. First of all, show that negative 1, 2 is a point on the curve. Well, we know that if this is a point on the curve, x has to be negative 1, y has to be 2. So we plug those in. X equals negative 1, y is equal to 2. Hey, we love algebra and arithmetic. 1 plus 2 plus 4, when we multiply all that out, is equal to 7, which is what we want that equation to be equal to. Part B, find an equation for dy dx using the procedure outlined in the previous problems. Your equation may be left in terms of x and y. A couple things to note. We've got x squared, which has no y's involved in it. We've got an x times y, which will involve the product rule, and we've got a y squared. The number one problem that people have with implicit equation and finding derivatives is forgetting an extra dy dx, which comes about from the chain rule as we saw in the earlier slide. The derivative will be derivative of x squared with respect to x, which is 2x. Derivative of xy with respect to x, which we just saw in the previous slide, was x dy dx plus y. Don't forget that we're going to subtract every term of that. So I put it in brackets there. And the derivative of y squared with respect to x is 2y dy dx. Remember, y is an implicit function of x. So when we distribute our negative, we get 2x minus x dy dx minus y plus 2y dy dx is equal to 0. As before, we want to try to isolate the dy dx term so that we can solve for it. When we move everything without a dy dx over, that's the y minus 2x part. So these two terms there. We're left with a 2y minus x times dy dx. I factored out the dy dx from the two terms that were remaining. We can divide by 2y minus x, and we get our answer, y minus 2x over 2y minus x. So then how do we find the slope of the curve at negative 1, 2? In other words, if we were to find a tangent line at the point negative 1, 2, what would the slope of that tangent line be? Well, we've got a formula for the derivative. That's what dy dx is. That will give us the slope of the curve. So all we got to do is plug in x and y into the equation we just found in part B. When we do so, we get 4/5. And as you can figure out slightly from this diagram, this graph, that's about what the slope of the tangent line would be, 4/5. Now, how do you find second derivatives? Well, what is a second derivative? A second derivative is just the derivative of the first derivative. It's a little bit more complicated for implicit derivatives, though. So let's do an example. Suppose x squared plus y squared is equal to 16. Find the second derivative and evaluate it at 3, 4. Well, the first derivative is one that we've seen before. Negative x over y. Right, we saw that on one of our earlier slides. To find the second derivative, we will need to use the quotient rule. We've got a top function, a numerator, x, and a bottom function, y. And I'm going to associate the negative with the x, which makes things a little bit easier. So to find the derivative, we do low d high, so that's y, times the derivative of negative x, which will give us a negative y, minus high d low, which would be a minus negative x dy dx, which turns into a plus. We're going to use the quotient rule here. Divided by low squared, which is y squared. We found our second derivative. Notice it's got that dy dx term in it. And if we wanted to actually find what this second derivative was in terms of just x and y, we would plug in dy dx is equal to negative x over y right here, as you can see. So how do we figure out what the second derivative is at 3, 4? We plug in x is equal to 3, y is equal to 4. When we do that, we get negative 4 plus 3 times negative 3 over 4. That's what dy dx is. All divided by 16. Simplify, we get to negative 25 over 64. Again, dy dx is just this formula right here. You can plug it in directly. Another example here. Find dy dx for x is equal to sine of xy. It's a little bit more complicated because we need to find the derivative of sine of xy. Notice there's an outside function, sine, and an inside function, x times y, which will require the product rule. So let's consider just that part by itself. The derivative of the inside function, x times y, is x dy dx plus y. That was on an earlier slide. Thus, the derivative of sine of xy would be the derivative of the sine part first, the outside function, which is cosine of xy, that's a chain rule issue, times the derivative of the inside function, x dy dx plus y. Overall, when we take the derivative of the left side as well, we get 1 is equal to cosine of xy times x dy dx plus y. Now this looks really complicated, and there are a couple of different ways that you could approach this. But the easiest way, I feel, is if you distribute the cosine of xy among your terms, the x dy dx plus y. When we do so, we get 1 is equal to x cosine of xy dy dx plus y cosine of xy. And now if we want to solve for dy dx, all we have to do is move the y cosine of xy over, subtract y cosine of xy from both sides, and then divide by x cosine of xy to isolate the dy dx. It's not too bad, but you got to get a lot of practice with it.